Welcome to Brain Vision.
To solve this question, it's a good call to use the following reference frame in order to apply Newton's second law. So, a very good reference frame for this question is the following. This will be my y direction and this will be my x direction. Then, using this reference frame, we will apply Newton's second law on both axes, the y and the x one. Then, we get the following. By applying Newton's second law to the y-axis, we get that the net force on the y direction is equals to the mass of the worker times its acceleration in the y direction. Note that the worker isn't falling inside the house and nor flying away. Therefore, it's standing still in the y direction. So, the acceleration in that direction is equals to 0. Then, the net force in the y direction is equals to 0. But the net force on the y direction has two components. The normal force, which points to the positive direction, according to our reference frame, so normal, and a portion of the weight force is also pointing in this direction. Which portion? This one. The weight force can be decomposed as two forces. One pointing in this direction, which I will call the y component of the weight force, and another one pointing in this direction, which I will call the x component of the weight force. Then, for the y direction, Newton's second law, we get the normal force minus the y component of the weight force is equals to 0. Then, the normal force is equals to the y component of the weight force. Now, we apply Newton's second law on the other direction, on the x direction. This tells us that the net force on the x direction is equals to the mass of the worker times its acceleration. Now, the worker isn't climbing further the roof nor slipping down the roof. It's standing still in this direction too. Then, acceleration in the x direction is equals to 0. So the net force in the x direction is equals to 0. But the net force in the x direction has two components too. One of them is the frictional force, which is pointing to the positive direction of the x direction. So, frictional force. And the other component is the x component of the weight force, which is pointing to the negative direction of the x-axis. Then, minus the weight component x, and this is equals to 0. Therefore, the frictional force is equals to the weight force component x. But we know that the frictional force is equals to 390 newtons. Therefore, the x component of the weight force is equals to 390. Then, we have to discover now what is the weight of the worker. How can we do that? We can do that by looking at the components of the weight force. We have a rectangle triangle with the weight, which looks like this. The hypotenuse is the full weight force. This side of the triangle is the y component, and this side of the triangle is the x component. And we have a 90-degree angle here and a 36-degree angle up here. Why is this angle equals to 36 degrees? Well, just take a look at the figure. This angle is 36 degrees. At the same time, there is a right angle right here. Then, this triangle is a rectangle triangle. Therefore, if this is the 90 degrees angle, this other angle here will be 90 minus 36 degrees, which is equals to 54 degrees. Then, look at the following. This angle between the roof and the y component of the weight force is an angle of 90 degrees. Okay? Then, what is this angle if we know that this one is equals to 54? Well, this full angle has 90 degrees. Then, this angle has 90 minus 54 degrees, which is again 36 degrees. So this is why this angle is equal to 36 degrees. Now, to calculate the x component, we can use the sine of 36 degrees, because the sine of 36 degrees is equal to the opposite side of the triangle, which is the weight component x, divided by the hypotenuse, which is the weight force itself. Then, the weight force component x is equal to the weight force times the sine of 36 degrees. Now, we use this equation here to get the following. 390 is equals to the weight force times the sine of 36 degrees. Then, the weight force is equals to 390 divided by the sine of 36 degrees. Then, finally, this gives us a weight force of approximately 663.5 newtons. Then, to find the mass of the worker, we have to remember that the weight force is given by the mass of the object times the acceleration of gravity. The acceleration of gravity near the surface of the Earth is approximately 9.8 meters per second squared. Then, 663.5 newtons, which is the magnitude of the weight force, is equal to the mass of the worker times 9.8. Then, the mass of the worker is equal to 663.5 divided by 9.8, which is approximately 68 kilograms. Note that there was no usage for this other equation from Newton's second law, and there is no problem with that.